Now, engineering is an interesting field unto itself. Many of you are formal in your nature. We engineers, our philosophy is if it works, it's useful. We may not know the theory behind it. Sometimes we backtrack and try to identify the theory, but sometimes the theory leads us. The first engineer, I think, identifies to us that we come from a wonderful legacy. We are descendants in our discipline of gods, because this gentleman was perhaps the first engineer from the time of Egypt. He was the high priest of the sun god Ra. Put that in your resumes these days. Of course, there's also a responsibility for us. The Code of Hammurabi noted that if you're an engineer, if you're an architect, and the building you built collapses and kills someone, we'll kill you as well. Happily, this does not yet apply to software engineering, for there would be very few of us left. Another engineer who influenced our discipline was Ismail Al-Jarazi, who is also considered the founder of robotics. He and his brothers wrote this incredible book, the Book of Knowledge of Ingenious Devices, in which he really is the first pattern language, because he described a number of common ways to solve common problems. From a legal perspective, the first engineer was an industrial engineer by the name of Charles Bellamy, and it came about entirely because of economic reasons. Here we are in the height of the industrial age. We're moving across the west of the United States, and we're building large structures out of newly found steel methods and steam and the like. And these things were failing and blowing up and killing people, which is never a good thing. So as a means of establishing responsibility, the state of Wyoming, of all things, established the idea of the idea of having licensed engineers. And Charles Bellamy was the first one. He came around the time where there were some major failures in dams and steam engines and the like. So the idea being that if we were to build such structures for which there is high risk, then indeed we want to have some sense of accountability. We are in the business of building not just software systems, but as I like to call them, software-intensive systems. And it's truly the notion of a system because it's this wonderful balance between the software and the hardware in the world. The idea of systems engineering came from Bell Laboratories. And this is in a time, really World War II, post-World War, in which, is the phrase I like to call it, all of modern software engineering was woven on the loom of sorrow. Most of what we know today and what we practice today came about because of the rise of conflict in World War II and the Cold War. We'll see this story again and again. So the idea that software was a part of a system is an important learning here. Now, worldwide engineering is what's called an occupational closure, meaning that to be a licensed engineer, you have to go through accredited school, you have to do testing, you have to go do continuing education. We software engineers, we take a lackadaisical view of that. We're not really licensed in that regard. Should we? This is a debate of some interest. I think some of us should be, some of us should never be. Some of us should probably never be software engineers, but that's another story into itself. But the idea of having apprentices is certainly one that we could follow. So if we consider back to our beginnings of our discipline, we must also recognize that ours is an astonishingly young discipline. The first computers were people, and for the most part they were women. The term digital was not coined until 1942, and the term algorithm was not coined until 1952. This was just before I was born, so this is an astonishingly young world. So where did the term software engineering come about? Well, many would say it came from the NATO conference. Notice, again, the connection to warfare, which was, 68 or so. It was a controversial name at the time, but as it turns out, there's an even earlier reference. There was an article in the 1966 issue of Communications of the ACM in which the president at the time used the phrase software engineering. We can go back even further, though. If you look at the archives in Silicon Valley, it wasn't really called that then there were some interesting classified ads. People actually wrote these things back in those days, before LinkedIn, in which someone was asking for a software engineer. Well, are these the first sources? No, it really came from Margaret Hamilton. She at the time was working on Skylab and the Apollo program. Before that, she was with the SAGE program. And she was one of the few people who was doing software work. Most of the work was driven by hardware. So to distinguish what she was doing from what the others were doing, she coined the term software engineering. And so I think we can rightfully claim that she is the one who coined the beginnings of our discipline. Is our discipline one of art or science? It's really both. As all three of these folks indicate, there's certainly an important element of art, and that's the creative part of what we do. But again, in this eternal dance of theory and practice, the theory also underlines what we do. Now, I've used the phrase many times that we are dealing with software-intensive systems. A system is one that has a number of forces upon it. And so like an engineer building a building, you deal with static and dynamic forces. In software-intensive systems, there are a variety of forces that weigh upon us. There is no perfect solution. There are reasonably optimal solutions at the time. And we have to, given the circumstances we're in, weigh these off for us. Some of these things deal with just the nature of our organization, the usual things of cost, schedule, goals, and like that. But increasingly, there are legal and social issues to what we do. As I often say, every line of code has a moral or ethical implication to it. It may not seem like it at first, but especially in the systems that work at global scale, the engineers who built them have implications for what they've done far, far beyond what they're doing in their cubicles. So let's begin this journey. We start, of course, with Babbage, and this is a time when software and hardware were not distinguished from one another. But of course, Ada, Countess of Lovelace, introduced the idea of really writing these things down as programmable elements. I think that was one of her most important insights. She, in some ways, her role in computing is overstated, but I think her insights are most profound because she observed that software is the thing that could make these machines incredibly fluid. Now, of course, the theory behind it was that of Boolean algebra, and even then we can see the hubris of our field. This was the laws of thought, not just the laws of logic. And so I think, again, we observe that there has always been this wonderful, if you will, concept behind all we do here, that perhaps the mind is computable, and perhaps that drives us in what we do in software. This was like a stand-up meeting for a Scrum, but this is actually the Harvard computers, and in fact it was called that. The computers were then he or she who computes, again mostly women, and these were the women. The woman in front is Annie Jump Cannon, who were the ones who took the work, the findings of the astronomers. It's the imposing gentleman in the back looking over them, glaring, and they would build the algorithms that would identify the patterns within that data. Indeed, some of the things that Annie Cannon had discovered back then in terms of measuring the luminosity of stars, we still use today. What's intriguing is that if you look at the way these teams organize themselves, they look an awful lot like Agile methods. So I think we can begin to identify some of the earliest ways of organizational software engineering, even back to her and Levin as well. As we began to mechanize what we were doing, then automation came into play, and all of a sudden we realized there were pipelines we could produce. This was, I think, from just right after World War II. No, I take that back. This was around the Depression time when this picture was taken. This was from a project, a works project organization, to build numeric tables in which the U.S. government employed hundreds, if not thousands of people to do calculations like this. And if you look closely, you'll see each one of the women has a calculator in front of them. There's a little inbox, and what would happen is you'd have a pipeline architecture. You would begin by doing a simple calculation. They'd pass over the results of that calculation to the next one, and it would go on down to the pipeline. So the problem is, of course, errors would propagate, but by and large, this was a very fast way to carry out those algorithms. Now, around that same time, there was this interesting work going on in process automation for building buildings. John Galbraith of the Cheaper by the Dozen fame, he and his wife did a lot of work in time and motion studies, and they developed a thing called process charts, which they use for things like bricklayers to say, gosh, if you're going to do this particular thing, then you need to orient your tools this way, your bricks this way, and we'll try to optimize the process of what you're doing, automating humans, if you will. Similarly, around that same time, Edith Clark was beginning to look at numerical methods for how we can actually measure those kinds of processes. Now, as our machines became more powerful, thanks to the 1910 census that led us to punch cards and the like, there were two transformational shifts. First, the machines became more powerful. Second, the machines became more expensive. And as a result, a lot of the work was done to optimize not for the humans, but for the machines themselves. Another staggering and subtle change here is you'd have to look at this picture and say, where did they hide the women? They put them in the back offices doing key punch operations, and it was the men who ran the machines. Well, not all the women were in the back offices, of course. Gertrude Branch began the notion of really the first outsourcing of work to do algorithmic work, and she actually built a company around it as well too. And Eckert also developed some notions, what we call them today pattern languages, for building punch card systems. A delightful book he wrote, and it's, again, solving common problems in common ways. You want to do this kind of accounting, you want to do this way, then you need to set up your punch card machines in this manner to do so. Well, again, we're in the era moving from these purely mechanical machines to electromechanical machines. The dashing young woman on the right, that's Grace Hopper, who was working with the Harvard Mark I at the time. And here is we began to see the logic engineering really coming close together with one another. George Stibitz produced a thing called the K machine. He sat down in his kitchen and made the incredible logical leap from Boolean's ideas to say these kinds of things could be mechanized in our relays. The K machine was the first half adder, and he began to realize that those kinds of mechanical operations that humans were doing could indeed be automated. Well, a little bit later, of course, what Stibitz did led to lots of different advances in machinery itself. Around that same time, John von Neumann was beginning to establish some of the theoretical underpinnings of our particular field. Of course, there was this remarkable happenstance meeting between him and the good folks building the Harvard Mark I. They were at a railway stop. At the time, John von Neumann was working on the Manhattan Project, and their calculations were an incredible problem. Feynman was the physicist. Feynman was also at the Manhattan Project, and he was responsible for managing most of the human computers because there were lots of chemical reactions and other reactions that had to be done. And so von Neumann made the connection between the mechanization that was coming about based upon the ideas of Stibitz and also that these things could be used for the Manhattan Project itself. Now, move a little bit forward in time, and you had, of course, Eckert and Motley, who were taking the fruits of what Stibitz had done and turning that into a company. And Grace Hopper was one of the first ones there. Now, unbeknownst to most until really the 1970s, similar work was happening in Europe, and in particular the UK. This is the Colossus. Colossus was designed by the engineer Tommy Flowers. It was based upon some ideas of another engineer, and those ideas were based upon the works of Turing himself. Turing, of course, had worked on the bomb, which was a way to accelerate calculations for cryptanalysis. And then taking those hints in what were called scripts, they could then apply those at scale to a much more complex problem, the deconstruction of the Lorenz code, which is the one that Hitler used. I can't believe I'm giving a lecture to computer science and I mentioned Hitler. That's weird. But such are the times in which we live. But the Lorenz code was particularly complex, and it was the Colossus that broke that code. Now, a lot of breakthroughs came about from the Colossus. Purely electromechanical machine, lots of vacuum tubes. Again, an interesting economic connection because this is the time where vacuum tubes were in mass production because of radios in particular. And Tommy Flowers and others realized those could be used as switching devices, which were much faster than the relays themselves. But this was a classified program. It was, in fact, not declassified until the 1970s. And as a result, a lot of what happened there did not impact the general field of computer science, although it did impact what happened in the UK, because a lot of the folks here went on to various places such as Manchester and the like, the Manchester Bay and so on. So we had Alan Turing establish some of those basic theories of what we were doing. Tommy Flowers I mentioned too. But then we had also Konrad Zuse. If the war had gone differently, then I'd be speaking to you not in English, but I'd be speaking to you in German. And we'd be talking about not the IBM 360, we'd be talking about the Konrad Zuse Z3 and the like, which were far ahead of their time. They were spectacularly architected machines. Now, we bombed the hell out of them during the Allied bombing, and so most of them were destroyed. Zuse went on to produce, however, after the war, some really fascinating work. In fact, he became a painter. He wrote some really interesting books. And one of those books was basically establishing the notion ahead of Deutsch, which suggested that the universe itself was digital at its basis, intriguing ideas. Well, advances moved forward after the war. We, of course, had the ENIAC, which started during the war, but never really went further. And the first programmers were, in fact, women. The programming in that case was done by plug boards. And so there's some great interviews of the women who did the ENIAC programming. Computer Museum and others have done some oral histories of them. But the process they went through was interesting because they were given algorithms, and they were the ones who had to figure out how to turn that into action, the automation itself. They actually wrote the book, the literal manual on the architecture of the ENIAC itself. These are some of the women for whom we have those interviews. Well, now we begin the first golden age of software engineering because there was sufficient power in our machines and sufficient complexity in our software that all of a sudden we needed to supply more discipline to it. So Tom Kilburn began really, I think, the discipline of programming itself, and Wilkes and Gill introduced the notion of the subroutine because they recognized trying to do these things just in a straight line was very, very complex. Now, back in its time, subroutines were considered to be architecturally very suspect because they cost you 2 or 3 machine cycles, which was very expensive. But the two recognized that we're not just building software for our machines, we also build them for the humans themselves. And this is, of course, when Eckert and Mach came on the scene. John von Neumann, after the war, he's in front of the, I think this is not the Johnny-Act, I forget which machine it is, but he began to take his ideas that he had learned from the Manhattan Project and apply them to large-scale software efforts such as meteorological climate models and also virtual life, as you will. This is around the time also when John Backus came on the scene. Because most of the systems in the world were written not in machine language, but now assembly language. And Grace Hopper, of course, had given us the notion that we could, go further in this and actually, put things in higher order languages. And of course, John introduced the idea of higher order languages in the form of Fortran, which in many ways was just a simple transcription of basic mathematical statements into languages, into the machine language, which was still very effective, but it's another rise in the level of abstraction. Remember I mentioned process charts earlier from Galbraith. Well, Goldstein picked up those ideas and recognized one way we could describe and reason about the things we were building is to take those process charts ideas and turn them into today what we call flowcharts. And he and von Neumann collaborated together to build what we have as flowcharts today. Around the 50s and 60s, we then had this interesting conclusion of mechanical machines, mechanical systems, and electronic systems. Here, you've got a punch card on the right side, and this is a whole system itself, and then hard disk on the other side. I think that one held about, 40 or 50 megabytes of storage in a ton or so. So megabytes per ton was a measure back then. And so here we are at a time where there was a great flourishing of ideas in our fields. There was a recognition that as we built these software systems, we kept doing the same things over and over again. And so it was time to, again, establish those layers. That's where operating systems came about. Grace Hopper, of course, went further, which he worked on COBOL along with others, and then came across SAGE. SAGE was an interesting problem. So consider the threat in the United States at the time, the height of the Cold War. We were worried about Russia taking its bombers coming over the Arctic and dropping nukes upon us. So the United States built this system called BEAMUS, the Ballistic Early Warning System, with a series of radar all across Canada. The DEW line is what it's called. And so you had a command and control problem of bringing in data from all these radars, and it came into a system called SAGE, a semi-automatic ground environment. This was the most complex software intensive system of its time. And some statistics tell us it took about 30 to 40% of all software developers in the United States to build this system. It was never used in anger, but it was used as a strategic method of combating what the Russians were doing. So here's an example where software is not just functional, but it also has political and social implications to itself. A lot of the things we did in SAGE, by the way, we still apply today. Look in the back there and you'll see these radar-like things. This is where the first graphics displays came into being, by the way. So this is also the time where computing broke out of its just business work into real-time kinds of things. And we recognized that our machines could apply to live in the world itself. Now, because our systems were becoming bigger and bigger and more expensive, the ideas of project management came into play, the ideas of time sharing came into play as well too. And of course, this all culminated in the 60s with the advent of the IBM 360, a flourishing time in our industry because there was a vibrant time with many, many hundreds of companies building computers, but it kind of all amalgamated in the form of the IBM 360 because all of a sudden now you could build software and preserve that investment and apply it to a number of different machines. So here we were truly at the height of the first golden age of software engineering because the ideas of information hiding and structured programming and modular programming came to be with people I'm sure all of you have studied. This is really where the first formal systems of our software methods came into play. Formal in the sense of taking these higher order languages and see if we can apply rigorous ways to prove their correctness. CA Hoare and Dijkstra and others in playing a role here. And of course, they made some important contributions to what we were doing that allowed us to build software systems of greater complexity and greater safety. This is Margaret Hamilton again, and it shows you, she's standing beside a printout of some of the software from the Apollo system. Software was a big problem. It's not something that just a single person could do, but it required a team of people. But the economics changed with the advent of the transistor, which then led us to micro-miniaturization, which led us to things such as the mini-computer, the mini-computer. PDP-11 Digital Equipment Corporation in particular. And now all of a sudden computing, the economics computing changed such that it could become personal. An individual now had the power in front of them that a mainframe would have had before. And so here we have again the ideas, especially in the 70s, of information hiding and the ideas of development process, Wayne Royce in particular. And I have to point out the work of Barbara Liskov and her ideas of abstract data types, which was, of course, ahead of its time, but was seminal in bringing us to the next generation of software engineering. These are some of the greats of that time. Ed Jordan, unfortunately, a year or two passed away, but they laid the foundation for what we can do today. Now, then, of course, micro-miniaturization continued and brought us the personal computer, and all of a sudden, thousands upon thousands of people to develop software. And these three strange guys came onto the scene, and we're at the beginning of the second golden age of software engineering, where we make the shift from algorithmic-based decomposition to object-oriented-based decomposition. And again, it was a very vibrant time. If you look at the literature, you look at what happened in that time frame, there were hundreds, if not thousands of us pursuing interesting ideas in those kinds of systems. Responsibility-driven design, OA&D, lots of folks were building some interesting things here. Of course, Barry Bain and his software engineering economics work and the like. Very, very exciting time for us. It's also the time we begin to see the interplay between software and business, and thus the forming of methods such as the ideas of case from James Martin, and also things like the Zachman framework, which were attempting to provide ways to bridge the gap between organizational processes and software processes themselves. Now, as software became more personal as well, we found that folks such as Keynote were observing that we write our software not just for our machines, but for our humans. And so the ideas of what we today call clear code, literate programming came about at his time as well too. And of course, Alan and his ideas with Visual Basic, introducing a whole new set of folks to programming, the ideas of visual programming. So here we are in, let's say, the late 90s or thereabouts, because the world of software looked a lot like this. I got my first email address in 1979, of all things. It was on the ARPANET. We had a little book, it was about 30 or 40 pages, that listed the email address of everybody in the world. It's pretty cool. Wish I kept a copy of that. Because the ARPANET was relatively closed. But as the ARPANET moved out into the world and it became public, then all of a sudden you saw people building systems like this. And so our software became larger, more complex. The ideas of methods such as Scrum and extreme programming and refactoring came into play. This is where we instituted the idea of the rationally unified process. And this is also the time when design patterns and the Gang of Four book came into play as well too. Interesting story, you may have heard of Reed Hastings, the guy behind Netflix. He was actually at Rational Software for a while, the company I helped found. He had started a small company in Boston, at Cambridge actually, and we bought his company. He realized he's a terrible manager, so he left the company about a week, took that money, and he developed this small company called Netflix. Another important seismic change, of course, was the iPhone, which now put power in the hands of individuals. And so we again saw an incredibly vibrant time, things such as Git being produced, places such as Stack Overflow being a place for developers to collaborate and the like. And so the landscape of the world looked an awful lot like this. We were beginning to see, for economic reasons, the network looked more and more like these small concentrations of power as we move toward cloud computing being developed by individual companies and the like. Another thing that happened is that as we started building systems of this kind of scale, it wasn't just about operations, it was also about development. And so the practice of DevOps came into play as well too. And so much of the world looks like this today, where you see these islands, and those are little purple circles, that have services that they offer up, services in a variety of ways, APIs, services, today we call them agents, if you will, that are delivered up, and that's how a lot of systems are put together. Indeed, this is the era of platform computing, and Jeff Dean and Jeff Bezos, the two Jeffs, are the ones who really pioneered that. Well, now we're in the realm of AI-assisted development. So the question to us on the table is, what does that mean for our industry? This is from Copilot. Let's pause and take a breath and say, what does that mean? We are seeing most of our history has come from symbolic approaches, but now we are intersecting with neuro-symbolic approaches. Now to get a context, let's take a look at the kinds of systems in which we can build with software itself. We are limited largely by our imagination. We as software developers take our imagination, which is really limitless. We try to turn those into executable systems. And there are a number of things that different kinds of systems along the way. The earliest ones were purely mathematically based, and so this is when we as a field were developing our fundamental kinds of algorithms. As we started moving this toward more business kinds of things, then it was a problem of truly the symbolic underpinnings. And so managing complexity, the first problems of the first and second generation, first and second golden age of software generation. As computing became more personal, and the problem was more HCI. As we moved to distributed systems, the problem was one of scale. And now as we move to what I call imagined realities, systems that really rival reality itself, then the problems are becoming more and more so ethical and social issues themselves. If I take my imagination at one end and raw running systems at the other, these are the things that make it difficult for us to progress from imagination. First are the laws of physics. You can't pass information faster than the speed of light. It's not just a good idea, it's the law. You can't do it faster. And so this has pushed our engineering into ways of looking how we can fabricate our silicon into smaller and smaller devices, living not just electricity but light. This is where quantum computing comes into play as well too. A lot of vibrant things happening in that space. The next thing that gives us pause is that of algorithms. The Viterbi algorithm is a good example of this. It was necessary to bring us forward in cellular communications. So the problem with cellular communications is that the world is a very noisy place. So how do I extract a signal from that noise? The Viterbi algorithm is an interesting way that allows us to algorithmically pull out those signals in a relatively efficient way. We knew theoretically how to do it, but we didn't know really how to turn that into something that was executable until the algorithm came to play. And such is the nature of algorithms. We may have the theory, but turning them to reality is sometimes very hard. Now, systems, though, are not just bags of algorithms, they are architectures, which means we have collections of things that work together, the data and the algorithms themselves. And so we see this coming to play in our large language model systems these days. They are underpinned largely by the transformer algorithms, but if you look at things such as ChatGPT and Gemini and Claude and all the others, they are much bigger than just LLMs. There's a whole set of design decisions built around them. And right now, that industry is struggling with what is the optimal in the sense of fast, efficient inferencing and low-cost kinds of things. We're struggling with what the right architecture itself is. But even if you have the right physics, the right algorithms, the right architecture, you've got to have the right organization to do this. Because you may start small with one or two people, but turning this into a system that can actually serve billions upon billions of people and actually make money requires you have an organization around it that makes it work. So if you look at some of the things like, again, the transformer architectures, gosh, OpenAI has thousands of engineers to actually build the system itself. And this is where organizational structures and patterns come into play to optimize what we're doing. It's also the case that the economics then play a role. The problem with contemporary AI is that it is sucking out so much energy and so much revenue right now, and yet it's spectacularly unclear if there is going to be a return on the investment. Is it economically viable to do this? We may want to do it, but in the long term, it may not be a sustainable thing. This is an unknown element for us right now. And in the end, the last thing that I think constrains us in moving our imagination to reality is our human issues. Can we build it? Should we build it? Is it the right thing to build, or that we build it? Who will be impacted by we build it, if we build it? Every line of code, you're right, has a social and ethical implication to it. Now, if you look at your traditional system, traditional project, it kind of looks like this. This is from Silicon Valley. I won't mention the name of the company. It's pre-COVID. Nobody's wearing masks. You see a variety of machines, Macintosh, Windows, Linux devices. Again, I had to ask the question that the folks that gave this to me, where did you hide the women? That's another lecture unto itself. I'm all about visualization, by the way, and so I'm delighted to see that both Microsoft and Amazon have their own particular ways of visualizing web-centric systems. This is, of course, not UML. It's their own architecture Amazon uses to describe the main design decisions for an AWS-based system. But if you look at it from different points of view, which is an important element, then you'll find on the left-hand side, well, actually both of these, this represents the services that each of those systems offer and their interconnections. Incredibly complex kinds of systems. But remember, there is more to the world of software-intensive systems than web-centric systems at scale. Lots more to the world. This is the architecture of IBM Watson's Jeopardy. It's a pipeline system. I went in and spent time with the team who built it after they won the Jeopardy challenge, and I documented it in the UML. Email me, and I'll be happy to send you the whole document on it. But the interesting thing you'll see in this is written in Java, huge systems. You can go into it and you recognize, gosh, look at the abstractions they have there. They have things like questions and answers and adornments and the like. It's really pretty straightforward and understandable. Not everything is a web-centric system at scale. Things like air traffic control systems are your classic embedded hard real-time system in which if it fails, people die. Most of the world's air traffic control systems are based upon designs from the Canadian air traffic control system built in the 90s and architected by a dear colleague of mine, Philippe Krushton, Built first by Hughes Aircraft. Philippe was the primary architect on it. Hughes won that particular contract, very successful, and it was carried over to many air traffic control systems throughout Europe. But again, it's a closed system, hard real-time, but it's not a web-centric system. It's also the case that in what we build, there are more stakeholders than just business stakeholders. You've got your end users, you've got your investors, you've got your developers, regulators as well too, the operators of the system. That's where DevOps comes into play. Which leads us again back to the notion of what we build, if it's economically interesting, is a software-intensive system. Now, there are many different ways to measure this system. One of these is based upon risk. This is the Z-axis. If people die, then that's a high-risk system. If you happen to miss the latest meme because Twitter was screwed up again, it doesn't really matter. That's the realm of good enough systems. Then we have the level of complexity, which is the Y-axis coming into us. If I build these things over and over again, your sort of next level kind of app for the phone, we know how to build these things. But if I want to build something like a robotic system that does surgery upon the human brain, well, we don't really know how to build those kinds of things yet. And so it requires some experimentation on our part. By the way, most of the co-generators for AI have built upon those former kinds of systems, for which there are tens of thousands, if not hundreds of thousands, of examples of those things out there, clear patterns from them. And the last one, the x-axis, is asking, is it disposable or is it durable? A lot of software is disposable. I write it, I throw it away because it's cheaper for me to do it again. Some software increasingly is durable, meaning there is economic investment in it such that I can't get rid of it. And so as you look across the life cycle of these systems, there's this interesting, this is true for all kinds of software systems, there are these three levels of activity that go on. The first is that of discovery, that's the red. Then there's a period of invention, that's the blue, where your architecture is established. Then there's the period of implementation. These three go on together, they overlap, and they go at various times. That leads to the ideas of architecture. Not all architecture is design, but all design is architecture. Architecture represents a set of design decisions that shape the form and function of a system where significance is measured by cost and change. That's my definition of architecture. And so every system has an architecture. In the beginning, it's a vision. But in the end, it is the result of the thousands, or not billions upon billions of decisions, small decisions made along the way. Some are intentional, some are accidental, most are emergent, but in time, all of them must indeed evolve. So architecture is the invisible stuff that adds positive value to bugs or the negative things that are quite visible. One of the things that Philippe, I think, pioneered in, which eventually came to manifest in IEEE ISO IEC standard 420080, I think it is, the standard on visualization, suggests that when you look at a system, you have to look at it from multiple points of view. So an architecture is not just a single flat PowerPoint diagram, it's the intersection of a bunch of these things together. And from that, we can realize there are multiple patterns we can find in each of those levels of view. Architecture, the bit in red, peaks at the beginning and dies out. The amount of code we develop starts at the beginning, begins to die out. But every successful project tends to have this biorhythm that goes along with it. And this is how we measure our organizations then. Some organizations are like, building dog houses. If it fails, you build a new dog house, you get a new dog. Some are like houses, a little bit more economically interesting. Some are like cities. Imagine going in and saying, I'd like to build this Hyperloop under the Eiffel Tower. You're going to have a lot of stakeholders who really care about that. Well, now we're in the realm of AI systems. And I define AI in this sense as systems that reason and that learn. You have to have both, or you don't really have an AI system. The idea of building automated systems that drive us goes way, way back. This is the system built by system. This is the idea of the mechanical knight built by Leonardo da Vinci. And his concept was, can we, fighting is a nasty, bloody, expensive thing. And can we build these mechanical knights to do this work for us? Fast forward to what's happening in Ukraine these days with drones, and you see the same kind of economics at play. Well, a lot of people would like to move us in the direction that we see in the movie Her, where we have sentient devices. Now, this may sound strange, but I believe that the mind is computable. Now, that has a number of implications. I don't think we have the right architecture to do so, but I believe ultimately we can get there. Folks such as Norbert Wiener, who came from an analog background during World War II, and who coined the term cybernetics, had similar concepts, although he wasn't digital in nature. And it really was the ideas of Herbert Simon and Newell who brought us the ideas of taking formal methods and applying them to the mind itself. And this was the first symbolic era of AI. But then we recognized in the work in the late 40s that neurons themselves were computational units. And so Minsky and others built the first neural net. This is actually one neuron with 5 vacuum tubes. It's for a system called the SNARC, funded by the military at the time, by the way. It was trying to do image recognition. Now, one of the things that AI did for us is it propelled the notion of machines such as the connection machine. Because even in the earliest days, in the 80s and 90s, they recognized that a lot of computation had to happen simultaneously. So Hillis invented that. We, of course, in the IBM system, threw a lot of hardware at it as well. And now we see the implementation of lots of specific machinery, TPUs and GPUs and the like, to apply this to our problem. What's interesting, though, is if you look at AI projects, they look an awful lot like the way we organize and run traditional symbolic systems. This came from Karpathy. At the time, he was, I think, still at Tesla, and he observed that when he builds systems, that you have not just continuous integration and continuous release, you also have continuous learning. So the problem here of integrating AI systems into symbolic systems is one of trying to integrate that learning simultaneously as well. Now, what I find encouraging is that the AI space is also beginning to recognize the presence of patterns. We're seeing even books about design patterns for AI systems, which is great. And of course, one of those patterns, the most important pattern at the time, is the transformer, which is an algorithm we see underpinning everything. But remember, there are some differences, because symbolic computation involves lots of calculation, lots of data, large volumes of data, and decision making. AI is largely about pattern matching of signals on the edge. Both are computationally equivalent. We know this to be true, but each have particular advantages and disadvantages. So most of us here are never going to write our own AI system from scratch. It requires incredible investment to do so. But a lot of what we're going to end up doing is bringing these systems together, the symbolic and neural systems together. Now, as the CEO of Anthropic said, AI will write 90% of our code in 3 to 6 months. I think he said that 9 months ago. I'm not sure, but there he is, 6 months ago. Mark, Salesforce said he expects 30 to 50% of their code to be AI generated. He said this earlier this year. I think they fired a lot of people, not because they were using AI or not using AI, but because they overhired during the pandemic. And then dear old Sam said, back in October or January, we know how to build AGI. Of course, he's got things like social networks he's doing because he sort of ignored the AGI stuff. There was a really fascinating report that came from Google recently that suggests that 95% of developers use AI. I'm not sure that's true. If I've used it once, does that mean I'm part of that 95%? 80% report productivity. Well, yeah, it's faster than Googling things, because Google search sucks, mostly. It's faster than going to Stack Overflow sometimes. 30% have no trust in AI systems. Well, I agree with that. I think 30% is kind of a low number. But at the end, look here, AI increased delivery instability, because it introduces lots of its own kind of problems. There's an organizational transformation, not just a tools problem itself. MIT reported recently a study, 95% of Gen AI projects are failing. Last night I read a report from Carnival Cruise Lines that they have initiated some 100 projects, and they have only 6 of them in production. There's a lot of tire kicking going on right now. And you see now work with trying to take prompting and turning these into real systems. But what do we call a language that has sufficient expressiveness, accuracy, precision, repeatability, sufficient to generate a repeatable, executable artifact? We call them programming languages. So Dijkstra wrote this wonderful article on the insanity of human programming languages. Go back and read it from, I think, the 70s. It is true, though, that AI coding will change the nature of software development, probably in the same manner as did the rise of higher programming languages. They will change the way we interact with our systems. Much like Visual Basic, they'll make it possible for some to develop software that could not have done so before. Will AI replace us? No, it's pretty much the same job as it was, it seems. And you must recognize that vibe programming and AI-assisted engineering are not the same kinds of things. Vibe programming is great. I want to sit down and say, I'm going to try this idea out. And it's like having an incompetent assistant at your side who is very energetic and very interested in finding things for you, often gets things wrong, but it's sure nice to have their energy around you. Y Combinator has some interesting schools right now. You might want to go see them. I think they're free. And if you look closely at what they're teaching that, oh wait, some of the fundamentals still apply. Testing, that's a really good idea. Configuration management, gosh, why didn't we think of that first? So let me emphasize again that there's a fundamental difference in software that's disposable and software that's durable. A lot of where I'm seeing vibe programming, AI-assisted programming taking place is in the prototypes, trying things out, and that's great, that's wonderful. Please use it for that. But those are disposable systems. We'll get to the place where these things like Cursor and the like are more dependable for us, but we're not quite there yet. So in this post-AI, post-quantum world, our symbolic systems are going to be augmented. The fundamentals are going to remain. There's much to be done in how to do these things. If I had another lifetime, I'd try to see if I could apply the UML to describe the architecture of neural systems. I'm off on other things right now, so I offer that as a challenge to some of you to do so. And what are those fundamentals? Building crisp abstractions, a clear separation of concerns, having a balanced distribution of responsibilities and simplicity. And we know organizationally, growing a system through the iterative, incremental, and continuous release of executable architectures. This is what software is all about. These are the fundamentals. And AI is not going to change that. Software is the invisible language that whispers the stories of possibility to our hardware. Software is the invisible writing that whispers the stories of possibility to our hardware. And you are the storytellers. So go off and tell some wonderful stories. I think we have time for some questions and answers.